Welcome to qnawire.
Here we're going to find the electric field at various radii away from the center of a long cylindrical hollow tube that also is carrying a wire right down through its axis. And the way we typically approach these, there are a couple things we need. One is Gauss's law, which says that the electric flux through a closed surface, and that is defined to be the projection of the electric field onto the normal of the surface all the way around, is equal to the enclosed charge over epsilon naught. So that is one of the tools we will use to find the electric field at various positions in this tube and outside of it. But we'll also need some information about conductors. The information we'll need, and some of the information we'll verify, is that the electric field inside of a conductor, which means inside the metal, is zero under electrostatic conditions, meaning that the forces on the charges inside have to balance themselves out. And they do that because the charges reside on the surface. So they scoot as far apart as they can get from each other. And that is typically on the surface unless they have some way to leave that surface. And one of the things we'll see is that this results in a discontinuity in the electric field perpendicular to a surface, whether that's the outer or the inner surface. So we have a hollow tube, and it is a conductor, and the wire inside is a conductor. So one thing we know for sure is in the space where you are looking at R between the inner and outer radius of the conductor, that the electric field has to be zero there. That is one thing we know for sure. So that goes with condition 1. What we're going to do with condition 2 is look at the surface charges on that hollow tube. So we're told that the middle wire holds a positive charge on it with a density of lambda coulombs per meter. And what that tells us then is in order for the electric field to be zero on the inside of the conductor, Gauss's law tells us there has to be an enclosed charge of zero inside. So that tells us that on that inner surface, there has to be a minus lambda so that Q enclosed when in the conductor is equal to zero, and therefore the electric field, and specifically the radial field, is equal to zero. And if the tube as a whole carries a net positive charge per unit length, that what that tells us then is that our outer surface has to have a surface charge density of 2 lambda. And once we see that, it is a matter of using Gauss's law to find the electric fields in the inner region with R less than A, and in the outer region with R greater than B. So that is what we are going to now do. For R less than A, the electric field times a small surface inside of the tube, which I can draw just so we can see what that looks like. It looks like a little cylinder with radius r, little r, and length L. Okay, so it's a little cylindrical surface. Okay, I'm not very good at my drawing, but that's an imaginary Gaussian surface, which is just there to help us imagine the electric field. And the electric field is coming out through the curved walls of that in the radial direction. So ER times the area, surface area of that, is the circumference times the length, has got to equal the Q total along that length over epsilon naught. And of course, where the linear charge density will come from is dividing both sides by L. Okay, so that's Q total over L, 1 over 2 pi r epsilon naught. And we can just put a lambda there for our linear charge density. So that says that the electric field decays in an inverse way as you get further away from the wire. And as we said earlier, in between the walls of the conductor, the electric field vanishes. And now for R greater than B, again, we can draw a surface outside the tube. Yeah. So there's our Gaussian surface outside the tube. And the only thing that's going to change is our linear charge density outside is going to still be, let's see. So we have a net of plus lambda. We have a surface charge density of 2 lambda. Yeah, so we better think through the enclosed charge. Okay, so if we think about that, here is our cylinder outside. And on the outer walls of the tube, we have plus 2 lambda. On the inner wall, we have minus lambda. And in the inner conductor, we have plus lambda. So we have to be a little bit careful. We've got 2 lambda times L. With the inner portion canceling. That makes sense because the electric field is 0 inside that conductor. Okay, so the way I interpreted this was the entire tube carried a lambda, which means the outer surface carries 2 lambda. I suppose there's another way to interpret that, but my way seems to be what they intended. So kind of working this out, we now have 2 lambda over 2 pi r epsilon naught. Okay, so let's make a plot of the electric field versus R. Okay, and we can't go all the way to 0. there will be some finite thickness of that inner wire. We don't know where it starts, but I'm certainly not going to draw the electric field going to infinity there. And out to radius A, our electric field decays, but then it drops abruptly to 0 and stays that way throughout the entire conducting tube. And then it jumps up all of a sudden to a little bit higher than it would if the tube had a net neutral plus and minus lambda on its two surfaces. It's got more on its outer surface than on the inner surface. And what we can now see is the discontinuity in the electric field happening in several places. We won't worry about the inner wire, that if it's a conductor, it will have a very abrupt positive discontinuity, which I'm trying to represent there. But at the first inner surface, there's a negative discontinuity, meaning that you have run into a negative surface charge. And then on the outer walls, there is a positive discontinuity, meaning that you have run into some positive surface charge at that wall.